this event, to convey one single message, and so that we create a big community. We're still kind of working on it, but it's going somewhere. And before I actually move my first slide, I wanted to mention that this event is going to be recorded tonight. So feel free to sing during the event if you want your voice to be recorded. No, just kidding, please don't. Just know it's going to be recorded. And so I have just a couple of slides I would like to show you. I'm really looking forward to this talk tonight. But I also would like to mention a conference upcoming called JLove. This conference is for free, and it's basically everything about the JVM. So there's going to be Java content, but also Scala content or Kotlin content. And it's on the 4th and 5th of December. And it's actually funny, for the first time I've seen this. The 2 days have scheduled that are on different times. So the 4th of December is a friendlier day for European time zones, whereas the 5th of December has a friendlier schedule for United States time zone. So I would say go check it out. The 5th of December is a Saturday. And yeah, let's see if you can participate. But I think the rooster and the speaker, the list of speakers is really cool, and the content's going to be good. We also already have a next global reactive meetup planned. It's coming on the 15th of December in about 3 weeks. And the speaker is Mary Grigleski. She runs the Chicago Java user group, and her talk is Thirst Quenching Streams for the Reactive Mind. So tonight's talk is also about reactive streams. So I like that we have this sort of theme going on. And I think this next talk from Mary is going to be more targeted towards, it's going to be more introductive about reactive streams. And I think it's going to be really cool as well. And finally, my last slide is about tonight's partner and enabler for tonight meetup is Codemotion. And I really personally love this conference. I love these guys. In fact, the founder, Chiara, she's Italian, like most of the crew, and Chiara and we went to the same school. A while ago, I'm not going to say how many years ago, but we went to the same school when we were kids. And as a testimony how much I love them, this is one of the first time I spoke to at Codemotion Amsterdam. I was younger and I had a lot more beard. And so I'm sure you've heard about Codemotion previously, but I would like to have Kelly take over and tell us something about Codemotion herself. So enjoy the night, everybody.
Thank you so much. And first of all, thank you for this opportunity in organizing this meetup with you. I'm going to share my screen in the meantime as well. I'm just going to let the last people in who are waiting at the moment. Yes, there we go. All right. First of all, welcome everyone. We are very excited to host this meetup with Kotlin Amsterdam, with Kotlin Reactive Amsterdam, and of course with you all. So Codemotion is an online platform with offline conferences for developers. So we are based on this map on the presentation you see where we've hosted conferences where we're based. And at the moment we are hosting conferences in Amsterdam, Berlin, Madrid, Rome, and Milan. However, due to COVID, unfortunately, our offline conferences weren't able to happen this year. So we decided to organize 3 online conferences, one for Northern Europe, one for Spain, and one for Italy, which is actually about to finish just now, the Italy conference. And hopefully we will definitely be offline conferences again next year, but we're also considering online conferences for next year in the spring. So keep an eye out for that. What we do as Codemotion is, of course, I told you about the events we're organizing conferences. We're doing online meetups, offline meetups as well, of course, when COVID will allow us to do it again. We've got free webinars, training programs, online hackathons, coding challenges, dev magazines, and we also have a dedicated page to communities on our platform, which is www.codemotion.com. Which is especially dedicated for the communities. And on this slide, you can see that we are publishing meetups. It's not just us who will publish meetups on there, but also the communities are organizing the meetups with us or even without us. So our developers have a wide choice of which community they're going to go and which meetup they're going to attend. So that's it for now. We are very happy to have you all here. I'm going to give the mic to Urs, sorry. And I wish you all a very lovely evening and enjoy the meetup. Thank you.
Okay, welcome everyone. I guess you can see my screen, so all is fine and dandy, so we can rock and roll, or let's say go with the flow. Tonight we will dive into Kotlin, SpringBoot, and reactive programming, and hopefully also experience the flow not only figuratively but also literally, as you will see. But first of all, let's introduce myself. My name is Urs Peters. I'm a so-called senior engineer because I'm already almost 20 years in industry. Did a lot of stuff with Java, Scala, and the last years with Scala. I'm also the author of various trainings, also a trainer. Love to do that. And the stuff I'm going to talk about tonight is not something I've done in my scratchbook. That's really battle-tested stuff I use in production. It's quite cutting edge, I have to say, but so far, what I will tell you is something that is really something that can hit the practical domain without any problems. So tonight, we will look at the 3 superheroes Kotlin has brought up, which are coroutines, channels, and flows. I would say these are the most powerful language features Kotlin has come up with. But first of all, because it's an online conference, you have this distance. I'm talking to my screen. Of course, I see some faces, but it's always really great to see real faces. I would like to know a little bit more about the audience, about you. So if you could turn on quickly your camera, then I will ask you some questions, and you can raise your hand if it's true or false. And first of all, I get the feeling that I'm talking to real people. That's quite nice. And second, I also get to know a little bit more about you. So if you are not scared or have a background that is, in that sense, presentable, not like mine, because my graphic is a full mess, so that's why I made this background. Please turn on your camera, and then I will ask questions and see how many of you have the answers. Okay, cool. Excellent. I see faces. Wonderful. Okay, so my first question is, who of you is coding Kotlin? Raise your hands. Okay, quite some of you. Cool, excellent. It's not really necessary for my talk. The examples I use are quite straightforward, so do not really need Kotlin knowledge. Who of you is programming in SpringBoot? That's even more than the ones that code with Kotlin. Fine. Then my third question, have you already done stuff with Spring Flux, which is the reactive extension of Spring? Okay, some of you have, fine. And who has already played around with coroutines? Okay, that's definitely the least. Perfect. That's what my talk will be about. So in that sense, I think even though you have played around with coroutines, you still can learn new stuff. If you haven't, then let's go ahead with it. And let's start with another question. What are coroutines? And I think more important, what are they good for? What kind of problem do they solve? But before we dive into coroutines, I want to make a little detour to really set the stage and make sure that we're all together on the same page. So we don't start out with fancy stuff, we start out with boring stuff. Most of you won't be surprised to see. So what I have here is some sequential blocking code. I have some random avatar I fetch here, then I do some email verification, and eventually I save a user in database. So this is the example which we will use actually throughout the whole presentation. So it's good to familiarize yourself with it. And I think we kind of agree with this guy. Come on, guys, this is so easy. Pity that you have to look at it because it's so well known, nothing special to talk about. So you might think that, okay, this stuff works. Why should I ever learn something else? And instead of giving you an answer, I will ask another question. How will this code perform under load? Because then you might realize why you should learn something new. So first of all, what I've prepared is a SpringBoot application where exactly this piece of code, as you can see it here, is depicted. So we have some remote service we call for the avatar, for the email verification, and then we save our user. We use a well-known GPA, that's a persistence framework. You most probably might be familiar with it. And we have some interesting feature built in here, which is delay. So I can artificially delay responses to my remote service. Okay? So let's see how this code performs. First of all, I'm doing a curl statement where I insert the user, and as you can see, I use a delay of 200 milliseconds. Let's do this sometimes and then figure out what the response times are. And as you can see, the response time is about 400 milliseconds. That's not very surprising because we do 2 remote calls. Each have a delay of 200 milliseconds. So this will be 400 milliseconds. Then we have some overhead. And this adds up to 400 plus something, right? Okay, fine. So far, so good. Now we create some loads on this statement. And this is my command line tool. I fetched some from internet. It's called Bombardier. It works perfectly. So what it does, it bombards my system for 10 seconds with this post call and a delay of 200 milliseconds. Are you ready for it? There we go. And because we have to wait, let's do the music. Okay, we got a reply. And as you can see, 50% of our requests, that's what you see here, will be completed within 400 something milliseconds. So fine, right? Nothing wrong with it. Let's do the same again. But now we do not introduce a delay of 200 milliseconds, but 1 second, 1000 milliseconds. There we go. Okay, you might remember the theme, it's Mission Impossible. I think this applies what we see here. Now 50% of our requests all of a sudden took 10 seconds. 10 seconds, that's 2020 unacceptable behavior. 10 seconds, only we increased our delay from 200 to 1 second, which is factor 5, but our waiting time has increased exponentially. How? How is this possible? In order to understand this, you have to look at how blocking application architectures work. You might know that, but I will quickly recap what is going on here, why we see this strange behavior. So whenever we get a request, we have a thread pool, which is populated with quite some amount of threads, 200 to 300 by default. And then such a thread will do some remote blocking call. And before it retrieves the reply, the thread can't do anything else because it's blocked. Then we do some database I/O here, the same. The thread will block until it has reply from the database. Eventually, we'll return the reply. What will happen if a resource becomes slow? What will happen is the following. Our thread pool, because new requests come in, will be exhausted quite quickly. And until a point where no more threads are available to serve requests. meaning that no new requests can be served until a thread is put back to the pool, giving exactly the error we saw that our user will be very unhappy because he has to wait, in our case, 10 seconds. Besides that, that's another disadvantage we have to face, is that we do not leverage parallelism. Everything is sequential. Making something executing parallel is hard. And especially in our use case, parallelism would be a great addition we could have. Okay, this problem is not really new. It has been addressed already some years ago with the upcoming of reactive programming, where they more or less exactly try to solve this problem. There are some other problems also, but this is one of the core problems that was tried to be solved. The question is, did they solve it? Let's figure it out. The example you see here is the reactive counterpart. So the blocking example before is now transformed into a reactive counterpart using the Reactor framework of SpringBoot. It is not conceptually exactly the same because here we make use of parallelism. And I will show the piece of code in my IDE. That's this one here. And I could ask you, where is the parallelism? And I think this is already quite a hard question to answer. When you just look at the code, you might probably not just figure out, even depending, of course, if you use this every day or not, but imagine if you're not a frequent user of Reactor, you might think, where is here parallelism going on? It is going on here with zip. So you have some operate that some kind of magically gives us some parallelism. So far, so good. Let's see how our performance works with this approach. So here we use the Reactor example. We have again a delay of 200 milliseconds. And what do we expect? Do we expect a reply of a response time of 400 milliseconds or less? Of course, it will be less. Let's do it several times. Why less? Because we leverage parallelism. We do 2 remote calls concurrently, meaning that combined together, they won't take much more than 200 milliseconds. That's what you see here. So in the end, we have 200 milliseconds plus some overhead. So by now, just by using reactive, we already won 50%. It's kind of cool, even though I have to admit that not every business problem, of course, is suitable for parallelism. Now let's see what happens when we use load. So we do again 200 milliseconds, and then let's bombard the thing. Let's keep waiting time a bit easy peasy. Okay, as you can see, it takes about 500 milliseconds with a delay of 200, which is, yeah, maybe if you would do it again, it would be a bit faster, but it's within a reasonable range, right? The interesting thing, of course, is what will happen if we increase it to 1,000, like we had in the blocking example. Remember, here we had this 10 seconds for 50% of our user. Now let's see what happens now. Okay, look at this. Now our response time became 1 second. That's exactly what we would expect because we have a delay per service of 1 second. We do them in parallel, so we won't be able to get under a second. But the overhead is almost nothing. It's 140 milliseconds for 50% of our users. So we increase the performance of our system by using this programming style on the load by a factor of 10. Cool. How? How can it be? How does that work? So instead of having a thread reserved to handle my whole request, a thread will simply take the request, then do some async non-blocking network call, meaning it will drop the request to the remote service on the network socket, but then not wait for the reply, but continue doing something else. So that's why we also need almost no threads. Normally you have by default 1 thread per core. So I have an 8-core machine. So in that sense, only have 8 threads that do their job. Once our remote service replies, another thread will be notified that picks up the reply and offloads it to another network part, in this case the database, and continues doing its thing. Then again, another thread, and by the way, it could always be the same thread, you don't know, but potentially could be always a different thread. Once the database has replied, we get a signal from the new IO that some reply has been sent, and then the reply will be sent. So in other words, if a resource is slow, then our system will not be blocked. Because no thread is blocked, there will always be a thread available to take on our request. Besides that, we now leverage parallelism. That's an addition we have, resulting in, of course, happier system users, because our system continues performing in all kinds of circumstances, also even when a resource becomes slow. So as a summary, what are the advantages of reactive programming? We get faster processing because of the parallelism. We get a resilient system because if a certain part of a system fails, it won't affect the whole of it. You can solve this with circuits break, all kinds of mechanisms, but when you do reactive, it's not really necessary. Except if you want to make sure that another system doesn't get too much load, but for your own system, it doesn't really matter. Your system stays responsive. Even though a resource takes 10 seconds, you can reply to a user within 500 milliseconds to say, okay, the system is slow, try it later again, because we always are able to react. Our threads can continue spinning. And what's also quite a nice side effect is that we use considerably less memory. A thread consumes quite some memory. And in reactive systems, you have few threads, whereas in the other systems, you could have hundreds, even thousands of threads that process requests. So, anything else to add? I think we solved the problem. We did what the reactive manifesto told us what it would achieve, and we did that. So the question is that really the case? So in order to answer this, let's take a closer look at what we've here when we look at the reactive implementation. The reactive approach is built on libraries, meaning that once you use such a library, it will kind of get viral all over your code. Once you go for reactive, all your code will be kind of polluted with their approach, with the abstraction these libraries use. For instance, we have the mono. The mono is an abstraction that gives you a value or an exception over a certain period of time. And then we have all these kind of combinators like zip, flat map to finally. You have to adhere. And one of the big problems is with reactive programming is that your business intent of your code can quite quickly get lost. This is a simple example. Real business examples are considerably more complex, and they're really kind of polluted with all these combinators and special methods used to deal with this reactive abstraction. That's one. So intent really suffers a lot with reactive. What's even more important is that this stuff, you might know that, is really hard to learn, for one. And for second, it is also really easy to shoot in your foot. A colleague of mine, Jeroen Rosenberg, has written a beautiful blog about how you can very quickly get into trouble using SpringBoot just by using it not the correct way. Your code will compile, everything looks fine, but you can have very, very severe side effects without even knowing. So what is the answer then? And by now, I really dare to say that Kotlin Coroutines have done a great job to give a considerably better answer than what we have by now with the reactive stacks. And of course, this is on you to judge. What are coroutines? In Kotlin, these are the concurrency building blocks for coroutines. And we will look into them in detail, but what they allow us to do from a conceptual level is we can express logic sequentially, like in the blocking scenario we saw in the beginnings. And the underlying implementation does the asynchrony. So it's not a concern of us, it became a concern of the language. And then we get code like that, which if you look at it without really knowing what's going on further, like the code we saw in the beginnings. And I think you agree with me that if you would show this piece of code to your boss, he would understand it. And if your boss understands code, then it really must be easy code. Now, let's add some spice to it. And now, all of a sudden, we also have asynchronous programming, meaning parallelism. So we set out requests for the avatar, for the email, then we wait for that. And all this happens without anything to block. So far so good. But we've also seen that we've introduced some stuff around, right? It's not exactly the same code. There is some things involved, like suspend, like launch, like global scope. And in the next slides, we try to give you an introduction of the minimal aspects you have to learn to deal with coroutines in Kotlin. And the good news is, once you learn these concurrency primitives, you can use them no matter which framework you have. Whereas in the reactive stack, every library will be quite different. So first of all, what are coroutines from a processing point of view? As you might know, computers have processors. They're quite heavyweight. PHP used to use processes to handle requests in the early days. Didn't perform very well. Now we actually use threads, and threads have quite a big memory footprint. It's 4,000 threads per 1 GB, quite a lot. When we look at coroutines, we can have 2.4 million for 1 GB. Nice. So it's some sort of very lightweight thread. And you might have heard of green thread, fibers, and so on. And this is the same concept that applies here. So let's compare threads with coroutines. Here we create some thread, and Kotlin has some nice helper methods to do that, so that you don't have to type new thread, new runnable, run, just here thread and the code block, and that's it. We sleep for a second, and then we print 1 second. And what we have to do here for this program to print after 1 second, we really have to join the thread, because otherwise this thread here, or the main thread would not wait for the thread that is created, so we have to make sure that they're joined together. The coroutine counterpart looks like that. And what you can do with coroutines is just create them. That's not possible. You don't have a construct and say, okay, create new coroutine and do something with it, like we do with threads. You always need to have a builder. And this is one builder, run blocking, which is a special one that bridges the blocking and the non-blocking world. Because the word blocking is in it, it's a good indication that you shouldn't use it in production. So mostly for testing purposes. Then we have launch, and launch really creates a coroutine, some sort of asynchronous process similar to what we do here with the thread. And now comes the beauty. We have a method which is called delay, but the method delay will not block these coroutines. No, it will suspend it, meaning that the resource associated with it, or the thread that will trigger this coroutine, can do something else. And after 1 second, it will kind of magically wake up and continue processing. So what's the difference between the two? That's more or less the same what we have just seen before, but with a quite significant difference. We create 1 million of threads and we create 1 million of coroutines. Let's process that because it's fun to see. This is thread versus coroutines. Let's start out with the many threads method. There we go. Oh, I should do some music because this takes long. Okay, it's already over. As you can see, we were not able to create more than 4,000 threads because by default the JVM is 1 GB, and we just saw that 4,069 threads fit in 1 GB, and that's quite correct. So you have a kind of confirmation of what we've seen before. Let's do the same with coroutines. Many coroutines. We created 1 million coroutines. And within no time, we have created 1 million. Then they will all sleep or delay for 5 seconds, and then it will print out their dots, and then they're done. So for coroutines, it's really a piece of cake to process. As a summary, our threading example exploded, whereas our coroutine example just did it without any effort. So now let's look at the core ingredients of coroutines, which are suspend functions. When you want a method to be able to be suspended, you have to mark with the suspend keyword. For the rest, it just looks like a normal method. There are some limitations with suspend function. One is that you cannot call a suspend function from a normal function. You always have to call it or within a coroutine. So here we have the launch method that creates a coroutine, and then you can call a suspend functions, or you can call a suspend function from another suspend function. That's a limitation you have to be aware of. How is this implemented? How is this suspending work? How is it possible that you do a call, then some magic waiting is happening, and once the result is there, processing will continue? That's magic, right? Especially when you've never heard of it. But when you take a look at what Kotlin compiles out of this, I think you can get a grasp of how they implement it. When this piece of code is compiled, Kotlin will compile an additional parameter into the dead method signature, which is a continuation. And this is how the continuation interface looks like. It has two methods, which is resume and resume with exception. So in our delay example, we will have some scheduler that schedules that after, say, 1 second, this continuation has to be set with the value, which could be, in this case, unit, or an exception if an exception would occur. And once this resume is called, some state machine within the Kotlin compiled code will make sure that the code processes at the point where it was suspended. This is more or less how they solved it, with a callback, but then not a callback you control, but a callback which is controlled by the language itself, so that you don't have to care about it. It's worthwhile to have a bit understanding of these builders, because they also come with certain objects you need to make this whole Kotlin thing work. We've seen these methods, embarking, launch, async. And what's more important in this example is that we have two other objects. The first is the coroutine context. Okay, what is coroutine context? It can be compared like a map where you can have different kind of properties. That's what a coroutine context is. So when you add a new element to a map, you still have a map. That applies also for a coroutine context. One of the key ingredients that's part of this context is the dispatcher. Coroutines are still executed by threads, because that's the execution infrastructure you have within JVM. So we need to rely on threads. So you will have to provide some dispatcher that does that. And when you don't do anything, you get the default dispatcher out of the box, which is as many threads as you have cores. And then we have the real beauty of actually this whole coroutine language concept, the coroutine scope. What does the scope do? The scope controls the life cycle of a coroutine, and most of all, it coordinates all the subcoroutines that are created out of a parent coroutine, so that you, the programmer, do not have to do this manual synchronization, which is very error-prone, hard to do, hard to grasp, hard to test. This is something the language takes out of your hands. And this term, you might have heard it before, is called structured concurrency. I assume this is still a bit abstract as I explained like that, so let's look at an example. Here on the left side, you have the threading example, and here on the right side, let's figure out what is going on here. So when we call run blocking, we have default arguments, and we have this block here with this fancy method signature, which is a function type with receiver. And what it actually does is that it changes the meaning of this. So within the run blocking code block, this relates to the coroutine scope here. And because it's the first scope, it will be the parent scope. From then on, I use implicitly this. So when I say launch, I actually say launch on this coroutine scope. And what I do then is I create a child scope. Then this child scope delays. And now comes the beauty. This method won't terminate before all the other scopes, in this case, the child scope we've created here, have been terminated. So there is no need for us to manually synchronize this code. It's just done for us. We also have the async builder. You have already seen some examples, so let's quickly walk through it because it's quite an important one. Sometimes you also want to have back a value, not only just start some asynchronous side effect, but also want to get back a real value. For this, we have async, which returns a deferred, and deferred has an interesting method, which is called await. So what we do here is we, instead of doing a launch, we create an async process, we delay it, then we return rabbit. And once this coroutine executes, the first suspension point will be at await, because await hasn't returned the result yet. So the code will kind of wait for these 500 milliseconds. Once this async method has a value returned, the code continues, and we're all fine and then. Making synchronization and orchestration of various asynchronous calls really a piece of cake. Instead of staying in this functional paradigm with a lot of flat mapping, also mapping, we now can set out various asynchronous calls and define ourselves where in the code we want to have a result to continue our processing. Makes programming really, really way easier. So far, so good. But in the end, this stuff needs to be available within a framework, right? Because we don't really use bare bone Java, Kotlin, Scala, whatever. You also use the Concurrency framework. And Spring did has put a lot of effort recently, and they still do, to bring all these beautiful concepts we've just seen into Spring and make it also be able to be used as if it was natively. So how do you port or enable SpringBoot with all these goodies we've just seen? So first of all, you need a Webflux project because coroutines will run on top of Reactor. And then the only thing you have to add are 2 more dependencies, which are the coroutines cores and coroutines Reactor. That's it. The only thing you have to do then is go and suspend. So you create your controls. I assume that this code looks familiar to you from an annotation point of view. You've done such controllers. Normally, you would define your functions here and then some code. Once you have added coroutine support to Spring, you can start suspending your functions and then use various method calls within this block that suspend to. As I just told you before, you cannot call suspend functions without suspending. You can only call suspend functions from another suspend function or from a builder. The builder don't have to take care of. That's something the Spring internals do for you. You just start out with a suspend keyword and off you go. But of course, only doing a delay for 1 second is not very useful. Normally, you will need database access. And there you also need to know stuff. As with Reactor, you cannot really use blocking JDBC-based persistency frameworks. What you should use with Spring is R2DBC. That's the reactive initiative for reactive database drivers, which you could talk easily 1 hour for the whole full night. But for now, just keep it. I keep it a term. And R2DBC is available for most databases, except for Oracle. They announced it in the spring this year, but so far they haven't delivered and they don't tell when to deliver. So bottom line is you cannot use your GPA or GDB based persistence frameworks. They heavily rely on thread locals, for instance, GPA. They do blocking calls, which would decrease our performance rapidly without taking special measures, which is exactly the same for every reactive stack you use, and especially also with Reactor in Spring. So if you use Reactor of coroutines, that's no difference. That's exactly the same. How do you create repositories? Also in a very, very easy and straightforward way. Instead of extending from CRUD repository or the Reactor CRUD repository, you extend from Coroutine CRUD repository, and then define your queries as suspend functions. And instead of returning an abstraction like the mono, you simply return the value or null. That's exactly what we want. We do not want to fiddle around with abstractions that just sit in a way. We want to get to the user object. That's what our business also wants us to do. For the rest, you have exactly the same capabilities like with normal repository. How about remote services? Also here, you would have to rely on an async client. Reactor offers you the web client, and you just can use web client or any other asynchronous client you like, as long as it's not some sort of blocking client like the REST template. These you should avoid. You can use that. We will see later on an example how you would have to use that, but it's of course not advisable because they make your method call, the thread that does the call, blocking. So this is a remote network call using the web client. And normally the web client doesn't return, of course, the value itself. It would return a mono or another abstraction. How does this work? How does this work in the context of coroutines? The only thing you have to do is you can have an extension method that stems from the Coroutine Reactor package, which transforms this mono into a concrete value. So never use retrieve.block. Very dangerous that they built in the API because this really blocked the thread. You simply use one of these conversion methods, and then you easily converted every Reactor abstraction into a coroutine. How this works, I would like to tell you in detail. I even have the slides, but I hide them because I think we won't have time for that. But maybe if there's time left in the end and you're interested how this is achieved, we can quickly walk through it. Up to you. So far, so good. Are there some limitations? They are, but these limitations are a question of time. When you use suspend methods, you can't yet use aspect-oriented programming. So if you define your point cuts, that will not work yet. What's also not yet fully accomplished are transactional annotations. As you might know, transactions is a quite difficult subject when it comes to reactive programming, because normally a transaction needs to be associated with a single connection, which then normally can be preserved on the thread, but because different threads participate in a reactive stack, it's hard to keep the same connections across different asynchronous calls. In Reactor, they solved this problem. For now, you can't use the transactional annotation, but you can use some sort of transaction operator. So you have a functional approach with it, and they're working on it. There was recently a great talk about their achievements in August. It's maybe worthwhile to have a look. For the rest, everything just works like the rest in Spring combined with Reactor when you use coroutines. Okay, so far so good. Now let's go a little bit deeper and look at our next very interesting abstraction Kotlin offers us. Say you have two kind of processes, they want to talk to each other. How do you do that? If you would have Java, plain Java, you probably would use a queue. How does a queue work? It's quite simple. You have here some producer thread, which puts stuff on the queue. You have a consumer thread that takes stuff from the queue. And now comes the nasty part. When the max queue size is reached, the thread putting stuff on the queue is blocked. That's probably why they call it blocking queue, I guess. The same goes for take. When the queue is empty, nothing else to take, the consumer thread is blocked too. So by using this queue, we definitely always waste one or the other thread, in the sense that they just stay there doing nothing. Kotlin came up with the queue you always dreamed of in that sense. So it's more or less the same. They didn't call it queue, they called it channel. And the channel has two interfaces, just to make it nicely clear on which side you're doing your thing. So you have the send channel on this side, and you have the receive channel on the other side. Then you have some coroutine there that sends stuff to the channel. You have a consumer on the other side, which does receive. And the beauty lies in the simple fact that whenever the queue size is reached, send doesn't block, it suspends. Same goes for receive. Queue empty, receive will be suspended. So no resource will be wasted when we use the channel. Let's look at some example. So here we create a channel. It's simply create a channel. That's what you do. Then you send something to the channel. So here we launch another coroutine. That's like launching a separate process from the main routine, so to say. It will send stuff to the channel. This one will suspend until something is sent, right? And eventually, it will print out these statements. And the last send won't happen because there is no receive. Nobody listens to the channel on this, in this particular setup, of course. So different kind of channels where this would work. But in this case, receive is required for this send to happen. So this is how this asynchronous connection between these two coroutines works like. They call this a rendezvous point. Of course, you have different methods on channel, like consume each, then it simply consumes whatever you put on the channel. So here we say turtle meets rabbit, then the channel is closed. That's another nice implementation about channels. They also will communicate channel events in that sense. So when a channel is closed, the consumers will be notified so they could stop their stuff or do something else. In this case, consume each will simply stop consuming and code would continue executing. What if you want to broadcast information from one coroutine to an amount of other coroutines? Then we would use the broadcast channel. So broadcast channel on the sender side implements the send channel interface. What we can do is we can open a subscription to the broadcast channel. That's what we do here. Then we get back a receive channel. And then the processing is the same. We do a receive, which will be suspended because we haven't yet sent a message to the channel. Our producer will send an item, which then eventually will be broadcasted to all different coroutines. That's an example. So here we create, instead of a channel, we create a broadcast channel, and we can define what kind of channel type we want. There are two kinds, conflated and buffered. What does conflated mean? Fancy word. It means that whenever a subscriber subscribes to this channel, it will get items from that point on in time. So items that were posted before the subscription won't be received by this client. Whereas when you have buffered, then the channel keeps a certain amount of items in memory. And when you do a subscription, you also would receive the ones that are still in the buffer. That's the difference. So here we have, again, more or less same. We have some coroutine we launch. We say send. We have a subscription, consume each. Two coroutines, open a subscription, and they will both get the emitted value here. And of course, turtle one could also be in a different order. We don't really know because we do not know for sure which launch will happen first. But what we know for sure is that only if all the launches have been completed, the run blocking would stop. That's again the structured concurrency feature we have out of the box. So once the channel is closed, this program will automatically exit. Another important aspect to know about channels. What we have here, we have again, so helper method in Kotlin, which says produce, which actually creates a channel and sends item to it. So we get here back a receive channel. In this piece of code, we we tried to get a handle to this receive channel, but then we implemented something like if arg size 2 return. So we don't do anything with this receiver. And that's an issue because channels are, as they call it, hot resources, meaning that they need to be taken care of. So their life cycle need to be taken care of. If we don't do anything with this receive channel, we have a coroutine associated with it, which won't be used, so we leak resources. Something you have to be aware of. And as you know, you can have a lot of resources with memory, but still you will leak resources, and that's never the aim. And that's one of the issues why Kotlin also came up with the other abstraction, because these hot, as said, it's like we're used to handle resources that need lifecycle care, like connections, like files, and so on. They all need to be opened and closed, and so on. It's very common. But of course, it would be great if you would have resources we just wouldn't have to care about, not at all. Okay, I think this slide is time for it, because now we leave the channels and move on to our last subject, because also time demands for it, which is how about processing a stream of value. Here we go with the flow. That's the abstraction Kotlin came up with. Flow. What is flow? It's a non-blocking stream of data. That's what flow is. How do we create it? With a builder, the flow builder, which then in its block will provide us with a flow collector. And actually what you do is whenever you emit a value to the flow, then a consumer would get this value. And the beautiful thing about flow is that it's asynchronous. So you can call suspend functions in it. So this is actually also the biggest difference to a collection. It is an asynchronous sort of collection in that sense, because suspend functions can be called within its builder. How to consume data from this flow? You do not have to consume it directly. You can also apply some intermediate operators, as they're called, to filter content or map it, so to transform the results of the flow. When you call the terminal operator, as it's called, then the flow will be activated and the values will really flow through the flow. Yeah, what makes flow so cool? Here is more or less the same example, but then we register some lifecycle methods in it. When we call filter on a flow, nothing will happen. The flow will only be triggered whenever you call a terminal operator. So in that sense, flows are lazy, you could call it, similar to, for instance, the Java streams that also need some final operator to really make the stream run. So in that sense, flow is a cold resource in comparison to channels, which are hot resources, meaning that they won't be active before you call this terminal operator, and they also won't be active once you've collected all the items of the flow. So in that sense, that's a really carefree resource which you can use, and you don't have to care anything about how to clean it up, close anything, and so on. That's why Kotlin will shift its implementations more and more away from channel to flow, because they have some iterated properties, as we'll see when we do some live coding in a minute. Let's talk about back pressure, an interesting subject. You probably heard about back pressure, I assume. I don't know if you still remember what it is. That's why I will tell it. Back pressure is a necessity that stems from asynchronous programming when you have a producer on the one side, a consumer on the other, and they are not as fast as the other. So the producer is very fast and the consumer is very slow. You can imagine that when you have asynchronous processes, somewhere the items will pile up, probably in the middle, in a buffer, and eventually the buffer will blow. So what reactive programming does is they came up with some implementation to tell the producer, hey, slow down, I can only consume that much. And they implemented this with some sort of back channel. So here you see this. When you have a publisher and a subscriber, you have the request method. So the subscriber signals to the publisher, You can give me 5 items now. Then the publisher tells, okay, there you go, 5 items. And then the subscriber has to signal again, okay, give me 10 items now. The publisher will deliver 10 items. This push-pull hybrid approach is tremendously complex when it comes to the implementations. Here we talk about a unidirectional stream, but you also can have bidirectional streams. So they have 2 back channels, information flowing all sides. Doesn't really make it easy to grasp what's going on. Flow, on the other hand, doesn't need this signaling with a back channel. Why? Because it relies on suspend functions. So here we have, in Kotlin terms, emitter and collector, which is the same like producer and subscriber. Here, emit simply will suspend until the collector has consumed it. Before, it won't be emitted. So by using this suspend infrastructure for Kotlin, makes this very complex back pressure approach by communicating demand via such a back channel simply unneeded, which is great. So I think we can safely conclude in this case, go with the flow. How is flow supported in Spring Boot? Before you can answer the questions, let's look again at the abstractions Reactor offers us. We have mono, which handles a value or exception over time, and we have flux. Flux is some sort of the collection counterpart of mono, so multiple values over time or an exception. Monos vanish when you have coroutines. We've seen that. So they disappear, they become a real T or an exception. And flux, as you might guess already, will turn into flow. So whenever you do some DAO, for instance, and you retrieve multiple items from a database, you would use flow. And you don't have to use suspend keyword here, because creating a flow is not yet a suspend operation. Consuming a flow is, but creating a flow not. That's why suspend can be omitted. So whenever you return multiple items, you use flow. And the beautiful thing is that you can return quite a large amount of data, so to say infinite large amount of data from a database, because they will be fetched piece by piece. Say you're stuck with a JDBC driver like I was, so this is code I had to write. We were stuck with Oracle and we still had to use a flow. Flow also provides with great builders to bridge the blocking with the non-blocking world. So you can implement this callback flow. We're not going to look at the details. I just want to tell it it's there. The only thing you have to take care of is when you use it, you have to use a special dispatcher for that. So normally you use these very precious dispatchers that do all the handling, one per core. And here you would have to use an IO dispatch because here some blocking will go on. So that's why you need such a dispatch. But still, it's great that they came up with a solution that you can quite easily port even blocking code into this flow reactive paradigm. Flow just works when used in a controller. It will be transformed into a flux if you are familiar with these abstractions. That's what it does. Like a mono is a T in a suspend function. Or your own flow using a flow builder. So what you do here is we create some sequence and then we emit some values. So do the emit yourself. Just works. Or you use something even fancier, which are ServerSentEvents. Have you heard of ServerSentEvents? You should have, because they're so old. They're already 14 years old. In 2006, together with the HTML5 standard, the very least. And I think ServerSentEvents is the most underappreciated, undervalued feature of HTTP used by now. We use it heavily because it's simple, it's extremely robust, and it allows push over HTTP, which is wonderful. So the code you saw is almost the same. The only thing you have to do is you have to say, it produces text event stream content type instead of JSON or whatever you told. And then you simply emit values. Here we emit ServerSentEvent object, which has two optional properties, which is an ID and an event name, and the data property, which is mandatory. How does it look like? Let's call the thing. Then you get a grasp of how the ServerSentEvents look like. So as you can see, you get an ID, an event, piece of data, and that's it. And by doing that, information can be easily pushed to various subscribers of your database, of your information system. Okay, considering the time, I will do some live coding and then I will round up. I hope that's fine with you, where I would like to bring together all of the superheroes, coroutines, channels, and flows. And I will use an example from a real-world example we've built for our client that involves all these different concepts. So let's start with a simple user flow where we could use, as you've seen by now, a DAO.findAllUsers, find all, because find all return a flow. But what does that give us? Let's run it. What's the URL again? It's users stream 0. Let's. Oh yeah, I see that because of our performance tests, my database is still a bit full of stuff. Let's do a restart. So what we see here is that we get back all the items, but the connection doesn't stay open. It will be closed because this flow is terminated. So that's not the behavior we want. We want to have a connection that stays open, and whenever a new user is there, it needs to be pushed. In order to achieve that, we would have to create our own flow. So now let's create some sort of logic that continuously pulls our database, and whenever a new user available, it will be pushed to the stream. In order to do that, we have to rely on a flow builder, and somewhere we have to call emit, right? Because this is when we send items back to the user, and we also have to make sure that this never stops. That's actually what we have to achieve. Okay, so what we can do here within such a build block is use state. State will nicely be preserved. There won't be any concurrency issues with state, which we be using here. Then we can create some methods, which we then will infinitely call. Let's call it take. And this take method will fetch some users based on some offset. And that's the offset we provided. The only thing we do afterwards is reassign the ID. By the way, it's not also we need to collect, of course. Then we have to emit our user. So once we've done that, the user will be set on a network and the client can consume it. And once we have done that, we can reassign our state with the latest user ID. So far, so good. If we would now call take, we would more or less have the same like here above. This system would terminate. What we can do now is say true, then call delay, and that's actually our polling interval. So nothing will block here. It will simply delay for a second, it will wake up, and then it will call take, and then this whole process would continue. So now we're actually polling our database every second to fetch the newest users if they are there. Let's see how this works, or if it works. Offset 0, there we go. These are our default users. So let's insert some new user. Let's do that. So you see it? Whenever we insert a user, it will be consumed. From an algorithmic point of view, this is quite a useless implementation, right? From a resource point of view, it's fine because we're not blocking anything. So these coroutines continue spinning. Our server just does nothing by using implementation. But if you have thousands of users, our database will probably won't be very happy if we every second would pull our database. So in our use case, we used in our client, we came up with an interesting solution for that. Where we have still a poller, we need something to poll. I just copy paste this piece of code. So what we try to do now is we want one poller per instance that can serve thousands of clients. That's what we want. But how do we communicate what has been polled in a database with all these clients? What do you think? A channel, of course. So we create here our channel, and what kind of channel you think it should be? Yes, you're right, a broadcast channel. And the information we want to broadcast is a user added notification. Then we have to say what kind of channel it is. We do a conflate channel, meaning once you subscribe, you will get these notifications. Here we have implemented such a poller, which just does stuff to be able to send notifications once new records are available in our database. So, and now, how do we integrate this in our final flow? The implementation looks very similar to this one. So I copy paste it, because it is faster, except for that we do not poll ourselves. But now we do a take for the very first time a user enters our flow, and then we rely on channel notifications. So we open a subscription, and that's what actually Kotlin wants you to do, is we say consume as flow. So I can easily transform a channel into flow. So these two just play beautifully together. When I'm on the receiving side, I can turn a channel into a flow. On the sender side, of course not, but on the receive side, I can. And that's what I do when I open a subscription. Then I can say consume or collect. And every time I collect, I can call take, and then real data will be fetched for a database. Let's see if this still works. Let's open our channel or our number 2 flow. So 8 have been added here. As you can see, because it's every second it does the polling, but now only a single process does the polling. So this our database is no issue, but all other kind of streams will consume it. Because of lack of time, I won't do the very last example. I just will tell you what it could even do. What's very beautiful about this approach we used is that we also could add some filters to that, so that depending on your need of data, you could filter it. So we could, for instance, filter on users with verified email addresses or without verified email addresses or any kind of other attribute you have in your data. So by simply adding this here as a parameter, we would be able that different streams can consume different kind of information, making, for instance, replication of data between systems a piece of cake, leveraging event-driven architecture in a very simple and effective way. Okay. This brings me to my conclusion of this talk. I really think that Kotlin is one of the few languages that was able to bring us the best of both worlds. So the very powerful and strong program paradigm, reactive program paradigm, but with the ease of use of the model we are familiar with and we are aware of. Whereas reactive programming was a specialism, and still is a specialism for a happy few of us in the industry, it is not really accessible for the mainstream program. And I really think with this approach, you can ride the wave without being the server that has to work day and night to know how to do that. Kotlin gives you the correct primitives on the right level to do very powerful stuff without all the nitty-gritty details you have to be aware. So, thank you. Before we go to the questions, I would like to point to the training I've authored and created, given many times by now. It's in the process of being certified by JetBrains. So should you want to know more about Kotlin, also about, of course, coroutines and more nitty-gritty details and even powerful stuff you can do with it, then take a look. And now, tell me what you still would like to know.
All right, well, thank you so much, Urs. We got some questions in the comments, so I'll read them out to you. If you have more questions, just feel free to put them in the comments and I'll read them out. So first of all, we've got Tobias who said, how about debugging the coroutines in Kotlin? More complex reactive structures might become confusing, right? What are the debugging methods and tools at hand for these?
Okay, the debugging tools at hand of this is that it's just debugging like sequential code. Kotlin, of course, is made by IntelliJ. That's the funder of Kotlin, and they made sure that your IDE just perfectly plays with all these aspects. So whereas debugging reactive code is just a nightmare, debugging coroutines is like debugging sequential code. Awesome.
Amazing, thank you. Rangel said, how about Elasticsearch? Could the coroutines be used with Elasticsearch? Sorry.
Sure. Elasticsearch is a system you would address via HTTP. That's normally the interface they offer you. And if you use an async HTTP client like the one I showed you, the web client, then you can perfectly use all the Elastic features at hand. It depends, of course, if you already have a client that is based on a blocking method, you still can do that. You just have to make sure that you use the right dispatcher. So you would have to use the IO dispatchers, and you don't have the benefit as if you use real coroutines. But what I've seen so far is also these clients also offer most of the time an asynchronous counterpart. And for Kotlin, for every async library, they made some coroutine glue for it, so that you can use it within the coroutine context. So the answer is yes.
Great. Then Jan Willem said, is MongoDB also supported as R2DBC database?
Yes, sure, yeah. It was one of the first drivers, yes. So if you want to have this push, what I do now with quite some complexity with a polling thread of a polling scheduled routine that checks whether new records are there and then broadcasts it to the streams. These you get out of the box with Mongo without this infrastructure. So Mongo really can push information to you. Postgres can do that too. Other drivers can do that also, but there's quite some caveats involved with it. But with Mongo, it just works perfectly, even simpler than what you've seen. Yes, great combination.
Okay, another question from Rangel. How do we write unit tests of a code with coroutines?
Oh, unit tests, it's beautiful. I have to show you that, because you just write unit tests as you write all the other unit tests you've written in your life. So I have, of course, written unit tests. Here we have some Reactor example of a test, just to give you a bit the discrepancy. So we do here some save method, and then you have a step verifier, then you have to create. So you have all kind of DSL things going on just to test a simple DAO. It's horrible, right? Now let's look at our user repository. The only thing you have to do in your test is call the run blocking builder. And from then on, you just test as if this is a normal repository. So also testing becomes considerably easier. It's not really easy, it's just as easy as it always was. That's what it becomes.
All right, thank you. And then Frey is asking, is an emitter of a flow aware of when a consumer of the flow isn't listening anymore?
Can you repeat it? I missed the first word, sorry.
Is an emitter, sorry.
Emitter, yeah.
Aware of when a consumer of the flow isn't listening anymore?
Yes, yeah.
Oh.
So in the example you saw, when the network connection is closed, at least when you relate to servers and events, this is perfectly bound to the network layer. So when the network connection closes, the flow will also be closed. So no resource will leak. That's correct.
Okay, Nikita is asking, did you also try Kotor? If yes, did you like it?
I haven't tried Kotor. I should have. I heard a lot of good things about Kotor. The only drawback I see with Kotor is that it's a complete new framework. It's fully based on coroutines, so it's really the core of Kotor is async programming in the purest form you can imagine. The only thing is that developers that know already a framework like SpringBoot cannot leverage their knowledge, and that's why I think the combination of SpringBoot with Reactor and Coroutines is very powerful, because you port all your framework knowledge, which can be quite in-depth knowledge you have. You can easily port it to a much higher level when you stick to this framework. But it's definitely worthwhile to look at it. They have great features, but of course not as many adapters with legacy system and the like in SpringBoot.
Okay, then we've got Alex asking, if Kotlin support for Springbok is still work in progress, did you encounter any limitations by the work in progress process? SpringBoot, sorry. After.
In March, there were still some limitations with the repositories and the querying mechanism, because it's really cutting edge, at least when it comes to all the additional features Spring offers. Like, for instance, what we've seen is that you define a method name, which will then be translated to some SQL query. These kind of features have recently been added, recently meaning in the summer. But by now, except of limitations I showed you, I haven't encountered any limitations for my work. So I'm using Kotlin for long. Also, reactive extensions we used recently. So far, no limitation, no bug, no issue. It's just really rocket solid.
Amazing. We've got some thank yous coming in. Christian says, great talk, thank you so much. And then we have Rashid asking, you explained how the subscriber of a flow can suspend its producer. I can understand how this works in one single running process, but how does it work in multiple processes like microservices when a REST controller returns a flow?
What you have with reactive libraries is that they are closely bound to TCP. So back pressure is something that is supported by TCP. And the only thing actually Reactive Stream do is they kind of bind their implementations together, so that from the TCP level, the back pressure will be propagated to your reactive stream. So this is how reactive programming works. Flow doesn't, in that sense, not work much differently, as in the sense that when you have two microservices that have some HTTP communication going on, the TCP back pressure applies. So when you have a microservice that pumps a lot of information to a slow other microservice, a consumer services, then or reads information from it, then the TCP back pressure kicks in when the consumer will slow down. So they're just perfectly bound together, and this applies for Flow. You also can look at from a different perspective. Flow in Spring Boot is not really a concept that is implemented bare bone. In Kotor, for instance, this, but Flow lifts on the Reactor. So in the end, it's a flux, which does all the nitty-gritty details of binding the TCP back pressure to the reactive back pressure. And Flow is just an abstraction on it to make it more bearable for you as a programmer. But in the end, it uses the same mechanism, which is already implemented there. And I could have showed you examples how this is working, but yeah, you have an hour, and an hour is not much. But maybe for another talk, I can really show with examples how this back pressure is working using using Flow.
Okay, then we only have one more question at the moment, which is from Avi. What is your take on Spring Boot plus Reactor plus Kotlin plus Spring Boot plus Reactor plus Java, pros, cons, advantages, and limitations?
Yeah, personally, I'm very positive about it. We've just, we've created a component which has to be very high available and low latency throughput, where we need parallelism and all the like. So recently we've brought assist production where we really leverage Reactor together with coroutines. we've seen that initially we did some stuff only with Reactor, with Kotlin together, without coroutines, and it got really extremely fast, extremely complex, hard to understand. Sometimes we were half a day just looking at some statements. Once we could lift it to the coroutine abstraction, it was just bearable again, in the sense that it feels like you program it the way you did before when you did all the blocking stuff. So personally, I'm really very positive about the result. There wasn't anything that didn't work or some weird errors or something alike. It's just a great stack. I really can advise you to use, and it's safe to use. The only thing is that Flow is still experimental, meaning that it's production ready, but APIs still can change. So sometimes you have to annotate certain parts of Flow with the experimental annotation. That's something you have to live with, but in that sense, it's production ready. That's also what they tell. It's not experimental in the sense of that's still thing can go wrong. It really works extremely well. But that's my personal experience. I'm quite enthusiastic about it. I don't have shares with JetBrains or the like. It's just really my personal experience, and yeah, I think I made my point clear that yeah, personally I have really very good experience using it.
Okay, he actually asked an additional question on this. He said, use Java with Reactor or use Kotlin with Reactor. Which one is your advice and why?
I think I can be also very brief on that one. Use Kotlin. We've had enough projects with Java, especially with Reactor, because the function support in Kotlin is so way better than in Java. That's for one, but also the language power you get using Kotlin is so tremendously better. Next week I do a talk about transitioning from Java to Kotlin, why you can evaluate that and what you win with it. We did that too. We had some Java applications, then we rewritten parts of them in Kotlin. Now we only do Kotlin. Now when we look back at Java code, we quite quickly get irritated. We think, come on guys, it's so complex. It could be so much easier, and not only easier, way safer, because you have the nullable types in Kotlin, you have immutability ST, but all these kind of features make your code base not only more readable, but also safer. Null pointer is something we don't know anymore. So my advice is go to Kotlin. And if you're scared, start testing with Kotlin and unit tests. It perfectly goes together with Java, and get a feel of it, what this language can offer you. And I promise you, you won't be disappointed. Otherwise, call me.
Okay, and then we've got Fabio asking, what do you think about Scala?
Scala, oh, that's an interesting, yeah. I was one of the first Scala trainers. It's the story I like to tell, because then Scala was small. I even was certified by Oderski. I had to go to Lausanne. So you see, I had a personal session with the master himself. So I was extremely pro Scala. I created quite some courses in Scala, Scala Basics, Akka, Advanced Akka, Akka Streams. So I really invested a lot in Akka. But my point is that Akka definitely has its sweet spot, but also here, to food yourself in the food is first of all extremely high, depending on which paradigm you go. If you go fully functional, if you go for cats, or go whatever. That's for one. For second, for enterprise programming, just do simple JSON translations, database stuff, maybe adopt to other systems. For instance, only choosing a JSON library in Scala is a tremendous task. I mean, you choose a library, you don't choose library, you choose a DSL. You have to learn and dive into to understand it, which is totally different than other DSL. So only get into it is a hard thing, even though it's beautiful. It's kind of prosa and code. Totally agree with that. But it makes simple things complex. And sometimes you need complexity for complex things. So there Scala shines, but this is not what I see in mainstream programs. So I think Kotlin is a way better fit for the, I call it Huistuin and Keuken programming. So just the normal enterprise stuff. Kotlin, I think, is a much better fit. And that was also seen in practice so far. We also have on our client, we have some Scala projects. We just rewritten what I've showed you today from Scala with Kotlin, and also the implementation in Kotlin got considerably simpler, better to grasp, even easier to test. Yeah, sorry for my investment in Scala, but that's the conclusion I draw today for, as I say, enterprise kind of programming problems. For other problems, I think Scala is still a perfect fit, but not for this kind of type of programming, in my opinion, what I've seen so far.
Amazing. Then we've got Frey asking a question. Any tips on how to migrate an existing blocking Java thread-based applications toward a Kotlin Coroutines application?
Yeah, here comes in the it depends word. Blocking, what is blocking? So if you do, for instance, HTTP, that's quite easy. You simply have to change your HTTP implementation with a async driver. If you use Spring Boot, then you do what we did in our presentation. You simply put in Reactor, you say suspend methods, and then you do some async calls. If you do a lot of database stuff, I still have to say that R2DBC, or let's say it this way. When you have to do a lot of mapping, I've seen in my personal experience that things like GPA, so these ORMs, object relational mappers, they're quite effective. So with few code, of course, they have their quirks and they have their miserable stuff, but just to make something work quickly, especially when it's, for instance, an administrative system, it's fine. We also do that. We use Kotlin with GPA and the blocking stuff for this kind of things. We use more the reactive part for the components that really need to perform, that need to be resource intensive, where we need parallelism to meet our performance requirements. That's what it's to use, because especially database access with AutoDBC, it's not as simple or carefree as when you use ORMs. Of course, maybe you might not like ORMs, then probably it's fine anyway. But if you want to get stuff quickly done, which doesn't have to perform tremendously, blocking is still fine.
Okay. All right, that's all the questions. We got a lot of thank yous. Kotlin is awesome. Thank you very much for the inspiring talk. And I got more about thank you for the explanations. Thank you for a nice talk. Thank you for a great meeting. So that were the questions. So thank you so much.
Thank you too.
And yeah, you can say whatever you want, but the questions are over.
Okay. Thanks a lot for joining my talk, and yeah, even listening longer to it than the timeline said. So great, thanks.
All right, thank you so much. Everyone have a really nice evening. Thanks so much for joining us, and we hope to see you again in the future. Bye-bye.
Bye-bye, guys.
Bye-bye. See you.
No socializing.
Yeah, it's horrible. It's horrible. That's the way it is nowadays. Hope it's
well, we can stick.
But
we can stick around until we get kicked out.
Maybe last comment. I really enjoyed that this is so much close to JavaScript and Angular now with those reactive patterns. It's just coming so close, so that I probably now can start Kotlin.
Yeah, cool. That's true. We also have now discussed should we use TypeScript or Kotlin for lambdas because we want to compile to JavaScript, and maybe TypeScript is also fine. They start to converge. Also, this whole async processing, they start to converge together. Yeah. From a language point of view. Yeah.
Thanks for the talk. It was
good. Thanks for joining. We'll talk without joining people.
So, Urs.
Yes.
How well do you think this will stand up if Project Loom becomes a success?
Yeah, I actually waited for this question. Yeah, let's. It's my personal take on it. I'm following Project Loom for quite some time. They started in 2017 or 18, so about 2 years ago, almost 3 years ago. I just had a talk on JFall some weeks ago. First of all, they do not tell when they deliver. When you look at the project page and the information you find on it, it's still really very basic. It's light years away from what, for instance, the whole Coroutine ecosystem does. So that's for one. I do not really trust them that it gets sufficient priority also from Oracle. It's kind of project which goes on and on and on, but never delivers. That's for one, but this could be solved, right? I mean, when you get more passionate, more money, then something could get out of it. What I personally think is more on a conceptual level. I think they didn't make the right choice, like I've seen, unfortunately, in many cases in Java. What they actually do is with Loom is that they try to make threads turn threads into coroutines. So they have the thread API, but they transfer them into light thread, green threads, so that all the async operations, so all the IO operations become async out of the box. For very many cases, that's fine. But when you address it on this level, what you won't get is things like async we've seen. They really need some different abstraction. Also, the structured concurrency is very imperative, very invasive. It's not really as hidden as in Kotlin. So I really doubt whether when you address it on this level, so on the thread level, whether you can get all the benefits you would get with what Kotlin does. Probably also will have to come up with some flow abstraction because yeah, it's not there. Then you use RxJava and you're still using these functions. So they're really lacking some issues there. It can solve a lot of problems for the normal Java apps that yeah, would get some performance boost, but not really leverage the full programming model you get with async, with flows, streams, and so on. This probably won't be there. So I think from that perspective, I don't believe in project Loom, but we will see.
So is there anyone left, or did most of you leave? Yeah, we're with
Most of
13
them
right now.
left, but I know there were some people, who are still talking. So when everyone is ready, I'm just gonna close the meeting. I'm not sure if anyone else wants to add something.
Well, I would like to thank Urs again. Like it was very nice. You had a great meetup. Thank you so much. And yeah, let's do this again in the future somewhere.
Sure.
Fun. Thanks, Urs.
Thanks for letting me talk. I also appreciate it a lot. And if there's something else, I would love to join. And physically would, of course, even be better, but we all have that. So that's a limitation we all have to deal with. But yeah, it would be great.
Thanks, Kelly, for setting everything up.
No problem at all. We hope to work together again in the future as well. So that will be amazing.
Yeah.
Cool.
Great moderation.
Everybody.
Fabio, Joost, Urs, thank you all so much.
Have a nice evening. Oh, thank you.
Thank you.
Have a lovely
Bye-bye.
evening. Bye-bye.
Bye-bye.
Same to you.